We have seen the dynamic source routing on the previous turn, and we have seen many disadvantages because the whole route was it used to be included in the data packet routing. This is the most popular protocol for ad hoc, especially mobile ad hoc network, and is known as AODV, ad hoc on-demand distance vector routing. A little bit complex protocol, and you need to pay a bit more attention while understanding this. And you can expect one question on this in your examination. As I told you, DSR includes source routes in the packet headers, and that is a huge overhead because if your route is long and a lot of time the nodes are changing, then their location may result into a large header, and particularly that is the overhead when your content of the data packets are very small. Now, what AODV attempts to do, AODV is attempting to improve on DSR by maintaining routing table at the nodes. Which instead of having routes in the data packets or in the packets, in AODV routing tables are maintained so that data packets do not have to contain the routes. Obviously, AODV retains the desirable feature of DSR that routes are maintained only between nodes which need to communicate. It's a kind of on-demand. So if A and D wants to communicate, only will think about finding the route and maintaining the route. Otherwise, not needed. Here also we'll use RREQ, route request packet, similar to DSR. Now, when a node rebroadcasts a route request, suppose there is a node A which forwards the route request to RREQ to B, and when B rebroadcasts it, so what B will do, B will maintain a reverse path towards A also, because A has sent RREQ to B. Now B knows that I can reach to A using this reverse path. So B in its routing table maintains a reverse path entry towards A. Obviously, AODV assumes a bidirectional link. When intended destination receives the route request, it will reply similar to DSR RREP route reply packet. So basic, you know, methodology is similar to DSR. Here also we are going to use control packets RREQ and RREP, which are going to be broadcasted and unicasted the way DSR used to do that. Route replies travels along the reverse path setup when route request is forwarded, because when you are forwarding the route request, here you have always set up the reverse path, and RREP are not required to be broadcasted. They will follow those reverse path setup. What are the properties of AODV? Route discovery cycle used for route finding. Routes which are active, which are getting utilized, are maintained. We use a specific concept of sequence numbers for loop prevention and for as a freshness criteria of a loop. So we'll discuss about this later on, that what is sequence number and how these sequence numbers are used for loop prevention and route freshness criteria. Whenever routes are not used, they get expired and they are discarded. So, and that's why we talked about the concept of active routes. The routes which are not going to be used for a stipulated time period, those routes would be discarded. And this, what this provides you, this provides that it will less number of stale routes, And then if less number of routes are there, less route maintenance has to be done. And then it minimizes number of active routes between active source and destination. Just a minute. मानस क्लास में है अब 11:30 ठीक है हाँ 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 ठीक What are other properties? AODV, as I told you, discovers routes as and when necessary. It does not maintain routes from every node to every other. And because we use the concept of active routes, routes are maintained just as long as necessary, not else. Now, this is important. Every node maintains a monotonically increasing sequence number, which increases every time node notices change in the neighborhood topology. So node will notice a change in neighborhood topology. Node will again go for the route request. And as and when a change is noticed, the sequence number is increased. So every node maintains a monotonically increasing sequence number. Obviously, it is initiated by one, initialized by one, and then gradually it keeps on incrementing. As I told you, AODV utilizes routing tables to store routing information. Please be with me. It's a little bit, I'm not saying difficult, but a bit complex. But it is easy to understand once you get the things. AODV maintains routing table for unicast routes and for multicast route. We are paying more attention to the unicast routes. So what is there inside the routing table? It is having destination address, next hop address, the destination sequence number, and lifetime of this route, after which this route will be deleted. So similar to our other routing protocol, we have destination. There we used to have destination network, here it is destination address, the next hop, the destination sequence number, and lifetime. For each destination, a node maintains a list of precursor nodes to route through them. So what are these precursor nodes? A node maintains a list of precursors. For each destination, a node maintains a list of precursor nodes to route through them. And that is, you'll see that will help in route maintenance. We'll come back to this later. Lifetime is updated every time the route is used. Every time a route is used, the lifetime will be updated. If route is not used within its lifetime, it will be considered as non-active and inactive, and the route will expire. The major thing to take away from this slide is routing table is having destination address, next hop address, destination sequence number, and lifetime. And for each destination, a node maintains a list of precursor nodes to route through them, which also help in route maintenance. When a node wishes to send a packet to some destination, so let's start the process. Send a packet to some destination. It checks its routing table to determine if it has a current route to the destination. If there is a route, packet is forwarded to the next hop using the routing table next hop entry. If no route is available to the destination, then it will initiate a route discovery process. Discovery process will be initiated. Now, what is route discovery process? The node creates a route request packet. Which node? Source node, which wants to have a route to the destination. Now, what is there in the RREQ header? It contains source IP address, source current sequence number. Every node maintains a sequence number. destination IP address, and destination sequence number. So what RRQ packet contains? Source IP address, no problem, you know that. Source current sequence number, it's a system variable, you know that. Destination IP address, you know, because you want to contact to that. And destination sequence number. Priya, how to know the destination sequence number?
So the sequence number changes for the packet transfer. So like, is it just the next sequence number than the source? So like, if so, sequence number right
No, no,
now is
no.
5, for
No,
instance.
no, no. Source and destination are maybe away from each other. And that destination might be doing many route discoveries. Fine. So it has got its own nearby topology and nearby nodes. So this is a system variable, means every node is having its own sequence number. If I notice any changes, I'll increment my sequence number. So every node will be having different sequence number depending upon the context. Are you getting the point?
Yes, sir.
So now the question is how to know the destination sequence number.
But for route discovery, we cannot know, right? Like, so we'll have to put something like infinity, or I don't know.
Now, there are two ways of doing the things. This is the important question here. Uh, you might have got, suppose you are in the system and destination is also in the system for a long time. Fine. They might have changed the routes due to their mobility. So you might be having a last known sequence number due to your previous, communication. So if you are having a last known destination sequence number of the destination, you'll put that. Fine. If you don't have any knowledge, then what you do, you'll put in place of destination sequence number arbitrary entry, which can be considered as unknown. Got the point? Hmm?
Correct.
Some vague entry which everybody knows that okay, this source does not know the destination sequence number. Okay. If there is any last known destination sequence number, that will be put. Okay. So in RREQ packet, we have source IP address, source current sequence number, destination IP address, and destination sequence number. The another thing which RREQ packet contains, you can see the RREQ header on Google. It contains a broadcast ID number. Broadcast ID gets incremented each time source uses RREQ. This is again a system variable, unique for every uh, system variable maintained at every node. So every time you do a RREQ broadcast, your broadcast ID number gets incremented. Now, broadcast ID together with the source IP address form a unique identifier for RREQ. Fine. Broadcast ID and concatenated with the IP address form it's a two tuple. Broadcast ID and the source IP address form a unique identifier for RREQ. Obviously, broadcasting is done via flooding, as we have seen yesterday. So, what are the entities? Source IP address, source current sequence number, destination IP address, destination sequence number, if known, okay, otherwise some unknown value, and the broadcast ID. Now, please be with me. Once an intermediate node receives RREQ, the node sets up a reverse route entry for the source node in its routing table. So what I mean to say that there is a node A and there is a node B. So suppose A sends a RREQ, fine, and as and when B receives the RREQ, B maintains. So there is an interesting point in AODV that it is having reverse and forward entries. What node B will do will set up a reverse route entry for the source node, for node A. And what this reverse route entry consists of: source IP address, source sequence number, which are part of RREQ, number of hops to the source node, and IP address of a node from which RREQ was received. Suppose RREQ has started from S to say node P and then node A. And this RRQ was forwarded, and reaches to B. Now what B will maintain? We'll see the RRQ, the source IP address in RRQ address, the source sequence number in the RRQ packet, number of hop to the source node, here 1, 2, 3, 3 hops to the source node, an IP address of a node from R, and then the previous hop, IP address of the node from which the RRQ was received. So this reverse route entry is made whenever a RRQ is received by any node. Think over it, and if there is any confusion, ask me. This is important here. Yeah, Priya, any doubts?
1 minute.
Should I explain it again?
Understood.
Okay. So we'll see the example also. Now using this reverse route, a node can send a RREP, because in any case node has to send the RREP also. So this reverse route entry will help unicasting the RREP route reply back to the source. Reverse route entry also contains the lifetime field, and after this lifetime expired, that reverse route entry would be deleted. Once RREQ reaches destination, in order to respond to the RREQ, uh, RREQ may reach the ultimate destination or any intermediate node. If any intermediate node knows the path towards the destination, any intermediate node can send a RREP, same as DSR. If intermediate node does not know the route towards the destination, then RREQ will reach to the ultimate destination. Depending upon the situation, the cases are going to be handled. In order to respond to RREQ, a node should have its routing table an unexpired entry towards the destination if it is an intermediate node, and sequence number of the destination at least as great as in RREQ. कि एक कोई नोड बीच में है, डेस्टिनेशन यहाँ पे है, now this node से intermediate node है, this is the destination, now RREQ is received, this RREQ is having a destination sequence number, this node is having an entry towards the destination in its routing table, this entry also having destination sequence number. If this distance destination sequence number and the destination sequence number in RREQ, if this is greater than or equal to this thing, then intermediate node will reply. Intermediate node will only reply if the destination sequence number which is entered in the intermediate node's routing table is at least as great as the destination sequence number which is there in the RREQ. This is the important point. And this is required for the loop prevention. We'll see one example. Ultimately, if there is no intermediate node which can reply, send the reply in between, then RREQ will reach the destination. If both conditions are met and IP address of the destination matches with that in RREQ, the node responds to RREQ by sending a RREP back by using unicasting, not flooding, because you do have a reverse path setup. If conditions are not satisfied, then node increments the hop count. Suppose it is an intermediate node, hop count in RREQ and broadcast it to the neighbors. And ultimately, the RREQ will make to the destination. Just a minute. Fine. So let's see this example. Suppose node X, S, needs a route to D. So node S will create a route request. What would be there in the route request? D's IP address, D's sequence number. If not known, then the last known. If last known is also not known, then some unknown entity. Source IP address, SS IP address, and SS sequence number, which is known. And right now, hop count would be 0. Fine. So this RREQ will be created. Node S will broadcast this RREQ to its neighbors. Node A receives the RREQ. It will make a reverse route entry for S. Now, reverse route entry, the destination would be S. Next here, the next hop also would be X, and hop count towards S is 1. That reverse path entry, reverse route entry is made. It has no routes to D, suppose. So it rebroadcasts the RREQ. Node A will rebroadcast it. Node C will receive the RREQ, makes the reverse route entry for S, destination S. Now the next hop towards S is A, and hop count would be in 2. That's a reverse entry. Suppose C has route to D, and sequence number for route to D in its entry is greater than or equal to D's sequence number in RREQ. Then C will reply. An intermediate node, as I told you, which is not the destination, may also send route reply, provided that it knows a more recent path than the one previously known to sender S. To determine whether the path known to the intermediate node is more recent, destination sequence numbers are used. The likelihood that intermediate node will send a root reply using AODV not as high as DSR. We'll come back to this later. A new route request by node S for a destination is assigned a higher destination sequence number. An intermediate node which knows a route but with a smaller sequence number cannot send the route reply. This is important. Whenever you send a route request towards the destination, that would be assigned a higher destination sequence number. An intermediate node which knows a route but with a smaller sequence number cannot send the route reply. That's the important thing. And that is what prevents the loop finding and can be used as a criteria for freshness. Node C receives the RREQ and it knows the route towards it will create a RREP. In RREP packet, it will be D's IP address and sequence number, SS IP address, and hop count to D1. And this unique RREP will be unicasted using the reverse route entries. Unicasted to A. A receives the RRP. Now, once A receives the RREP, it will make a forward route entry to D. Destination is D. Next hop is C. And hop count is 2. So see here, when you are receiving RREP back, you are making a forward entry. When you are receiving a RREQ, you are making a reverse entry. And both are working in tandem. And then it will be unicasted back to the S. When a node, what is the forward path setup? When a node determines that it has a current route to respond to RREQ, that is, has a path to destination, it creates RREP, route reply. What RREP contains? IP address of the source and destination. If RREP is being sent by the actual destination, the RREP will also contain the current sequence number of the destination, hop count equal to 0 and lifetime. If RREP is being sent by any intermediate node, RREP will contain its own record of the destination sequence number, hop count, its distance towards the destination, and its value of the lifetime of that route. So both cases can be there depending upon the situation and the context. When any intermediate node receives the RREP, it makes a forward path entry towards the destination. What forward path entry contains? IP address of the destination, IP address of the node from which the entry arrived, hop count towards the destination, and lifetime. To obtain its distance to destination, that is hop count, a node increments its distance by 1. जो भी hop count आ रहा है उसमें 1 बढ़ा देगा तो वहां तक की दूरी मिल जाएगी. If node does not use the route within its lifetime, that route will be deleted. After processing the RREP, the node's forward is towards the source. So major point here is, if you see closely, that when you are sending RREQ forward, the reverse entries are being created. When finally RREP route reply is done, using the reverse entry, we are making the final forward entries, actual routing table entries. Node S receives the RREP here, makes a forward entry to D, destination would be D, next hop A, and hop count 3. And in this way, node S, node A can have its forward routing table entry. It may so happen that you may receive multiple RREP from different paths. Node may receive multiple RREP for a given destination from more than one neighbor. What node will do will only forward the first RREP it receives. It may forward the another RREP if it has a greater destination sequence number or a smaller hop count. क्योंकि दोनों ही सही हैं, उससे better है. पहली आरआरपी उसने ब्रॉडकास्ट की, दूसरी आई, या तो उसका डेस्टिनेशन सीक्वेंस नंबर ज्यादा है, माने कि ये ज्यादा फ्रेश है, और इट इज हैविंग ए स्मॉलर हाफ काउंट, छोटा पाथ है उसके पास, तभी वो दूसरी आरआरपी फॉरवर्ड करेगा. रेस्ट आर गोइंग टू बी डिस्कार्डेड, and this in turn will reduce the number of RREP propagating towards the source. And once receiving the first RREP, source node can start transferring the data. Data delivery is simple. You have a forward route entry today. Next hop is a hop count 3. It will send to A will send to C, and C will send to D. In this way, data delivery can be done. So I've given a pictorial description of this, and some more information you can see it, just a detail of what we have discussed. I just want to tell you about the role of destination sequence number. Suppose this is the situation: A, B, C, E, and there is a path from C to D. Suppose somehow this link is broken, and assume that A does not know about this link, broken link between C and D. So link broken has been the way we do it in DSR. We send a root error message whenever we find that a link is broken. This root error message is propagated, as we have seen. When a next hop link in routing table entry breaks, all active neighbors are informed. Link failures are propagated by means of root error message, which also update the destination sequence numbers. So we do use root error message, and then destination sequence number, ये ज्यादा ताजा है, destination sequence number increment होगा और उसको भेज दिया जाएगा, root error message. When a node X is unable to forward packet P from node S to node D on link XY, it generates a root error message. Node X increments the destination sequence number for D cached at node X. So node X है, and there is a node S, there is a node D, there is a link Y, there is a node Y. So S to D, we have a route. X in its routing table might be having D's entry, the next hop Y, and so on. Suppose X is unable to forward packet using Y, this link will be considered as broken. So X will generate a root error message. X increments the destination sequence number of entry for D, puts that destination sequence number in RERR, root error message, and this root error message will get propagated. The incremented sequence number is included in root error. When node S receives the root error, it initiates a new route discovery for destination D using the latest number. Fine. When node D receives a route request with destination sequence number, latest destination sequence number, node D will set its sequence number to this latest one unless it has already larger than n. In this way, destination sequence numbers keeps on incrementing, and which actually uh, are indication of which is the fresh route or which is the current active route. Use of destination sequence number provides you this particular facility. Now, I was telling about this. Suppose C to D link is broken and this is not known to A. Assume that A does not know about failure of link CD because Suppose RERR sent by C is somehow lost. It can happen. Now C performs a route discovery for D. अब सी डी के लिए रूट डिस्कवरी करेगा, कोई लिंक ब्रोक चला गया है, हो सकता हो डी भाग गया हो, यहाँ पहुंच गया हो, उसके बीच में और नोड आ गए हों एक दो. So C performs a route discovery for D. When C performs a route discovery, RREQ भेजा जाएगा, ये RREQ A तक भी पहुंच जाएगा. सपोज ये यहाँ से पहुंच गया RREQ CEA. अब A को रूट एरर तो मिला नहीं था, A को रूट एरर मिला नहीं था. A को क्या लगेगा? A is having a path towards D via, क्योंकि A को तो मालूम है कि मेरे पास D का पाथ है AECD, और वो C को बता देगा यार तुमको जाना है तो यहाँ से चले जाओ, because I have a path via C. Node A will reply since A knows a route to D via node B. उसको तो B का ही पता है कि B से जाएंगे तो हमको नोड मिल जाएंगे. फॉर इंस्टेंस CEABC. अब वो कहेगा कि यार B से चले जाओ, B आगे बढ़ाएगा, C कहेगा नहीं यार मेरे को तो पाथ ही नहीं है, फिर ये रूट रिक्वेस्ट चलता ही रहेगा, ये लूप बन जाएगा. Now destination sequence number avoids this. If you have a destination sequence number and as soon as A replies, because this RREQ would be having higher destination sequence number, higher than what A is having destination sequence number for D, so A will not reply. A will not do the RREP as we have seen in the previous slide. RREP intermediate node तभी भेजेगा जब उसके पास जो RREQ में डेस्टिनेशन सीक्वेंस नंबर है उसके बराबर या उससे ज्यादा डेस्टिनेशन सीक्वेंस नंबर की एंट्री होगी. So in this way, sequence numbers in AODV are useful for avoiding this. There can be some optimization which we can do. Expanding ring search. Normally we don't send RREQ arbitrarily for all the network. RREQ are initially sent with a smaller TTL. The next phase some larger TTL, then larger TTL. So as to avoid, so as to limit the broadcast. And we can do the same optimization in DSR also. If no route reply is received, then we can increment the time to leave field for the next round. As a summary, routes are not included in the packet headers. Node maintains routing table containing entries only for routes that are in active use. At most one next hop per destination maintained at each node. Unused routes expire even if topology does not change. We just have to maintain the active routes. Any questions from anybody? Any questions? If there are no questions, we can stop. And Priya, please inform me about the timing of the tomorrow class. Okay?
We can continue with the same time.